I've almost finished my floating point binary multiplier, so this is it here. Now it's not completely finished, but I thought I would just show you what I've got at the moment, and I'll let you know the problems that I'm having just now, and I'll hopefully have this finished within the next day or so. So it's going to take two 32-bit floating point binary inputs, so that's the inputs here, and it's going to give a 32-bit floating point binary output here. And I've also got some of the flags set here, so I've got the not a number, we've got the plus infinity, minus infinity, the plus 0, minus 0, the positive overflow and a minus overflow, positive underflow and a minus underflow. So whenever I go through the full multiplier section, which I will go through over the next week or two, you'll understand what these are for in case you don't understand them now. So let's drop inside and we'll have a quick look. So this is the circuit here, so zoom out, this is the entire circuit. So we start off with the left hand side here and we've got our input. So what we wanted to do is take the two inputs and just stick them into 32-bit registers, just so we can control the flow of the information through the floating point unit. So we've seen these registers before, so these are just got a set and the enable, and this is the enable section here. Now the next part is the easy part to implement, which was the sign. So the sign bit is relatively straightforward. If the sign is a 0, then it's going to be a positive number, and if it's negative, it'll be, if it is a 1, it'll be a negative number. So whenever you multiply these two together, in order to get the right output, you just need to use an exclusive OR gate. So again, we'll talk about that whenever we go through the full video series of the design of this multiplier. But it's quite straightforward, that bit. Now the next part is the exponent. So whenever you multiply the two numbers together, as you've seen from the multiplication video, we're going to have to multiply the Mantissa, that is the significand, and also add the exponent. So we've got this section here, and this is a little section. I'll maybe zoom in a little bit to see a little bit better. Okay, so this is section here. So we're coming in, we're bringing the exponents in here, and we're going to subtract off the value of 127 in order to get the right bias. Now there's also an option here of subtracting off 126 because we might actually be using a normalized number, so we've got a choice here whether we subtract off 127 or 126. Now the numbers we get here, we're going to add them and we'll take them out here as the sum of the exponents. Let's head back up. So that's going to come out here, and we're also going to have to change the exponent because whenever we do the multiplication, we potentially have to float it by 1 bit. Again, we'll get into that in detail when we go through the course, but you've also seen that whenever we did the actual multiplication video. Now there's one other possibility for the exponent changing, that is if there's a rounding issue, so the very last bit of the 23-bit Mantissa has to be rounded and all the other bits are 1s, then the rounding could potentially pass all the way up through, right up to the exponent. So we have to cater for that by adding potentially an extra 1 in here for that rounding, and that comes from a different part of the circuit which we'll see in a minute. And we head here and we take the output, and this is the final exponent output. Of course, we have to add the 127 back onto it in order to get the correct value. In fact, looking at this now and explaining this to you, I can see an issue with this, and the reason why I think I've got a problem, it just came to me this very second, and that is that if it's going to have a subnormal number and it's e to the 126, I wouldn't be adding 127 back onto it. So that's something just off the top of my head as we're talking through this. I've just noticed that might be an issue, and it might be a solution to my final problem, which I'm working on at the moment. Anyway, we have this output here, and this is our exponential. This is our exponent. There's another couple of options here as well, because we need to test for an overflow. So if we multiply two numbers together and it's greater than the number that can be represented in the 32-bit register, then it's going to give us an overflow, and it will actually it will just flag up overflow, and it's up to us whether we want to decide to generate that as a plus infinity, or also the opposite as well for minus infinity. Now we're going to have the same thing for the underflow, but this doesn't work at the moment. This is not how it's going to be done. Going to be slightly different, but I'll be working on that over the next day or so. So let's head in and we'll have a look and see what else we have in it. So this is the exponent, okay, and it's going to come out, and finally it will be fed into an output here, and it will be all fed together to the final output. But before it can go there, we want to do the floating and in fact I'll explain the Mantissa bit first of all, because that's quite straightforward. So this one here, so we're going to have to multiply the Mantissas, okay? So first of all, we want to check and find out whether the numbers are normal or denormal. So we can do that check here. So we're going to just check what comes in with the exponent. If the exponent comes in and it's all zeros, then we're going to get a high output here. And if the exponent comes in, it's all isn't all zeros, we'll get a low output. So we say 0 for denormal and 1 for normal, okay? And it's actually slightly different because I've got these NAND gates, these inverters in here, but they may well come out before the end of the final version. So we've got a test here for our normal and denormal numbers. So having tested that, we can then take this test out and feed it into the next section. The next section is going to be then multiplying the Mantissas together. So in order to multiply the Mantissas together, we're going to extend the 23 bits to the 24 bits. Okay, so this is the bit extension, and whether we extend it using a value of a 1 or a value of a 0 will be dependent on whether they're actually the number that comes in is a normalized number or not. So if it's not a normalized number, the extension will be a 0, so we'll pop a 0 in here. And then whenever we head out here, we take the two 24-bit numbers and we multiply them together. Now whenever we multiply them together, we'll get the lowest significant 24 bits will come out here, and the highest significant 24 bits is going to come out here. So let's head on and we'll look at the next section. Okay, so we've already been in there, so let's head on and we'll go to this section here. So we're also got to take account of, as I say, the exponent floating, so the changing of the decimal point for the exponent, and also the possibility of having rounding. So we'll look at that in this next section here. So again, this is just a cursory look over it, and I'll go through it in a lot more detail, okay? But it's just to let you know that I'm actually still here. I haven't been putting videos on for the last week or so because I've just managed to get myself a new computer, so I've got a nice fast i7 with 16 gig of RAM and a nice solid state drive, so things are running quite well. So we're going to work out whether the exponent has to float or not, so that's this little section in here. So we're going to test for the highest significant bit, and if the highest significant bit is a 1, then that tests it here, and the 1 is if the highest significant bit, which is obviously the 23rd bit, so that's 23 in hex, okay, 16 in hex is 23, so it tests that highest 23rd bit and sees whether it's a 1 or not. If it is a 1, this would go high, and we would have an output here, this ext, okay, and if it was a low, then it would be inverted to a high here, okay, and we say that this extension here would actually happen. So we'd actually get an extra 1 on the float bit. So again, we'll go through this whenever we go through it in detail, but all this is basically doing is just shifting the point, 1 point. And you've seen that we had to do that whenever we did the multiplication. And that's the float coming out here. And that float comes down and comes back into the exponent and changes that exponent value. Now the Mantissa section here, what we want to do here is we're going to shift the Mantissa either to the left by 1 value or no values, depending on a couple of things. So it's going to be dependent on whether this ext has been set. So this ext was set by checking the 23rd bit just in the last section. But lately I've come through and I've added another couple of options here, because when I was trying to multiply together a normalized number with a denormalized number and I get a denormalized result, I was getting a problem with the Mantissa, and I realized that I wouldn't want to shift the Mantissa by 1 bit if that were actually true. So I've added this little section in here, and then finally we come down here and we take our bits and we then chop off the first bit, so we end up, so it's in effect dropping the 1 off if it's a normalized number, and this was left with our final Mantissa here. So I would imagine the speed I've gone through this here is probably quite difficult to follow, but we will go through and we'll go through it in some detail over the next week or so. So let's get into the rounding section here. So we're going to take in the least significant bits, so that's the 24 least significant bits, and also the 23 most significant bits. Now we chop off all of the bits here other than the most significant bit in this. So we're basically looking at the most significant bit of the last 24 least significant bits. So we're interested in taking that one because that one's going to tell us whether we're going to have to round. Okay, so we're going to, if it's a 1 in that instance there, we're going to round that up. So that can potentially pass up into the Mantissa. So the thing is, whenever we add that up, if it passes all the way up through the Mantissa, so the Mantissa in that case I believe would all have to be 1s. In that case, if it passed all the way up through and it came out here, there was a carry, this is a carry out that would have to come out and head off to the exponent. Okay, but if that isn't the case and it doesn't carry all the way out through here, then there's no extra rounding within the exponent. But also here as well, whenever that carry out goes high, if it does go high and there is an extra addition onto the exponent, then that has to be taken care of here as well. So we take care of that here with this little feedback to get the extender, and could potentially shift this by one position. And then we're going to chop off the 24th bit here, so we'll be left with the final Mantissa. I'll go through this in more detail whenever we actually go through examples, and you can see this working all the way through. I have these little probes in, and we'll go through an example and you'll see every single part of it as it works all the way through. Okay, now the last bit that we're interested in here is the output, and this is something I thought was going to be quite straightforward, but it turned out I've spent probably just as much time as messing about with the output here as I have with all of the rest of it. Now I'll get into this here and we can have a little look, see what's inside it. So this is it here. I'll maybe zoom out a little bit. So there we have it here. Okay, now the main thrust of this section here are these 3 blocks, and I've used these 3 blocks in order to look at the possibility of having all ones in the exponent or all zeros in the exponent. And we've seen there when we went through this course so far that these are special cases. So I wanted to take care of these special cases. So rather than, say for example, having an input coming in and it's a zeros coming in and you're multiplying it by a number, rather than that actually running through the process of doing that through the floating point unit, what we can do is just work out the answer to these at the beginning and just put them in the output. And I thought this would be quite straightforward, and it's turned out to be quite challenging sometimes, and I'll get into the details of that whenever we get through the course, but let's drop in here. So what we have here is the infinity times a number. Okay, so we're going through the different options here. If you had the value for your y coming in and it's a 0, so if one of them is a 0 and the other one value here is infinity, okay, so that's the value for plus infinity, which is the hex value for it is 7f8 and the 6 the 5 nothings. So it tests for infinity, and it's going to test here for the whether the sign actually, so it's going to test whether the sign is equal to a positive value, in which case it would go to plus infinity. And there's another option here if the input was, the other input was a y was a 0, and we go to plus 0, and there would be a possibility for this going to a nan. So there's various possibilities, and I worked through all of the possibilities here in order to get all of these outputs. Okay, and again, I thought whenever I started this was just going to be an easy, quite straightforward section, but it's turned out to be quite challenging. Now I'll show you another part of it here, the output. So we do the same thing with the 0, so it's going to be 0 times each of the numbers, and we go through the options of what the possible outputs are going to be. And finally, we begin, and we're looking at, this is a bit I'm still working on now, so these two bits work okay, but I'm still working on this bit. So this is the overflow and underflow. So the overflow works fine, but I'm still working on the underflow. So we've got the overflow, which comes in, and there's a possibility for a positive overflow or a minus overflow, and again the positive overflow and minus underflow. But the overflow works okay. I'm still, as I said, working on the underflow. Now the final part for this here is that we're going to use this output section to override in effect what the floating point unit does. So the floating point unit will work through in a particular format, but whenever it works the value of say 0 times a number out, it'll actually give you, if I just left it, it would just give you the wrong answer. So I've left it like that because what I was going to do was just design it so that we can put in all of get all of the correct outputs whenever we have the special values coming in, and then design the floating point unit so that if those values come up, it just overrides whatever the floating point unit is doing, and or in this case the multiplication unit is doing, and it just puts out the correct values. So we've got the correct values here then for the plus infinity, minus infinity, plus 0, minus 0, not a number, the overflow plus overflow minus, underflow plus underflow minus, and this will just pass these values out. If any of these go high, then it will override whatever would have come out from the normal root of the multiplication unit, so that would be that normal root there. But if we have any of those special cases, then these don't get put through and these numbers do get put through. Okay, so as I said, it's pretty much working other than just one thing, and that is the only one thing I can't get it to do is when I multiply a normalized number by a denormalized number and the result is a denormalized result, the exponent is the wrong value. So I'll say that once more. Whenever I multiply a normalized number by a denormalized number, and I get a denormalized result, then the exponent is the wrong value. And that's the only last thing I have to work out, because it works now through working multiplying normalized by normalized, and you get normalized numbers, both plus and negative, they work fine. And when I multiply normalized number by denormalized numbers and I get a normalized result, positive, negative, that works as well. But the last bit, as I said, when I get a denormalized result, the Mantissa is okay, but the exponent's wrong. And as I said, from doing this video, I think I've just worked out why, and it was this addition of the 127. So I've left that addition of the 127 in, irrespective of what the answer is going to be, normalized or denormalized. So that might be the problem. So I'm going to crack on now. I'll see if I can get this fixed. And as soon as it's fixed, I'll have to come up with a testing system to test the unit. I'm not sure exactly how to do that, but I need to test every single input and every single multiplication and see that it gives the correct value for the output. No idea how to do that, but stay tuned and I'll find out, and whenever I find out I'll tell you, and then you'll know as well. Okay, so thank you for listening. I'll get you in the next video. Goodbye.